The service voltage readings provided indicate a potential safety issue. The low B ground and C ground readings suggest that the grounding system is not properly bonded. The 480 volts the ground reading indicates a possible open neutral or other improper wiring. These conditions can create electrical hazards such as electric shock, arcing, overvoltage and equipment damage. The electrical contractors claim that the installation is okay based on information about three-phase transformer configurations is likely inaccurate. The readings provided do not match any standard transformer configuration. Suggested actions are: firstly, contact the electrical contractor again. Express concerns directly to the electrical contractor and provide the voltage readings obtained. Explain the safety risks involved and request immediate action to rectify the situation. Secondly, document concerns. Keep a record of all communications with the electrical contractor and any observations or measurements that were made. This will serve as evidence if necessary. Thirdly, consider independent inspection. If the electrical contractor is not responsive or cooperative, consider hiring an independent electrical inspector to assess the installation and confirm concerns. Fourthly, contact the local inspector. As a last resort, it may be necessary to contact the local electrical authority to report the safety concerns and request an inspection. Be professional and respectful in communications with the electrical contractor. Provide clear and specific evidence to support concerns. Offer to assist the electrical contractor in troubleshooting and resolving the issue if necessary. If possible, document concerns in writing and request the electrical contractor's response in writing. Safety is paramount. It is a responsibility to ensure that the installation is safe. In regards to understanding three-phase transformer configurations and grounding, it's crucial to understand the fundamental principles of three-phase power systems. Three-phase power is used to efficiently deliver electrical energy, especially for industrial and commercial applications. It involves three alternating current voltage waveforms that are offset by 120 degrees from each other. This configuration provides a more constant power delivery compared to single-phase power. There are several common three-phase transformer configurations, including YY, Delta Delta, Y Delta and Delta Y. Each configuration has its own characteristics and is suitable for different applications. In a Y configuration, the three-phase windings are connected in a Y shape with a common neutral point. The voltage between any two phases is the line-to-line voltage, while the voltage between a phase and the neutral is the line-to-neutral voltage. In a delta configuration, the three-phase windings are connected in a closed loop forming a triangle. The voltage between any two phases is the same as the winding voltage. Grounding is a critical aspect of electrical safety. It provides a low impedance path for fault currents to flow back to the source, allowing overcurrent protection devices such as circuit breakers or fuses to quickly disconnect the circuit and prevent electrical shock or equipment damage. There are several types of grounding systems, including solid grounding, impedance grounding, and ungrounded systems. Solid grounding involves directly connecting the neutral point of a transformer or generator to ground. This provides a very low impedance path for fault currents, resulting in fast clearing of ground faults. However, it can also lead to high fault currents and potential equipment damage. Impedance grounding involves inserting an impedance, typically a resistor or reactor, between the neutral point and ground. This limits the ground fault current to a safe level, reducing the risk of equipment damage while still providing adequate protection. Ungrounded systems do not have a direct connection to ground. While they can offer some advantages in terms of service continuity, they are generally not recommended for safety reasons, as they can result in overvoltages and make it difficult to locate ground faults. Proper bonding is also essential for electrical safety. Bonding involves connecting all non-current carrying metal parts of an electrical system, such as enclosures, conduits and equipment frames, to a common ground point. This ensures that all metal parts are at the same potential, minimizing the risk of electric shock. In the case of the 480 volts MCC, it is likely supplied by a delta Y transformer. The delta side is connected to the incoming three-phase power, while the Y side provides the 480 volts output. The neutral point of the Y winding should be solidly grounded to provide a low impedance path for ground faults. The readings provided suggest a problem with the grounding or bonding of the system. The low B ground and C ground readings, both at 15 volts, indicate that these phases are close to ground potential, which is unexpected in a properly grounded system. The 480 volt ground reading suggests that phase is floating at the full line-to-line voltage, which is a dangerous condition. A possible cause of these readings is an open neutral connection. If the neutral connection is broken, the voltage on each phase will no longer be balanced with respect to ground. This can result in some phases having a high voltage to ground while others have a low voltage to ground. Another possible cause is a high impedance ground connection. If the ground connection is not solid, the impedance will limit the flow of fault current, resulting in a higher voltage to ground in the ungrounded phases. It is also possible that there is a problem with the bonding of the system. If the metal parts of the MCC are not properly bonded to ground, they can become energized, creating a shock hazard. To troubleshoot this issue, a thorough inspection of the grounding and bonding system is necessary. Firstly, verify that the neutral point of the transformer is solidly grounded. Secondly, check the ground conductor for continuity and proper size. Thirdly, inspect all bonding connections to ensure that they are tight and free of corrosion. Fourthly, use a multimeter to measure the voltage between each phase and ground at the MCC. If the readings are significantly different from the expected values, this indicates a problem with the grounding or bonding system. In addition to the grounding and bonding system, it is also important to check the wiring of the MCC. Verify that all connections are tight and that there are no loose or damaged wires. Look for any signs of overheating, such as discoloration or melted insulation. If any problems are found, they should be corrected immediately. Regarding the electrical contractor's claim that the installation is okay, it is important to challenge the claim with the evidence that was found. Request documentation or calculations that support the contractor's assertion that the grounding and bonding system is adequate. If the contractor cannot provide satisfactory evidence, it is necessary to insist on further investigation and correction of the problem. It is important to document all communications with the electrical contractor and any actions that are taken to address the issue. This will provide a record of the steps that were taken to ensure safety. If the electrical contractor is not responsive or cooperative, it may be necessary to escalate the issue to the local electrical authority. The local authority has the power to inspect the installation and order any necessary corrections. Remember that safety is the top priority. It is not worth risking personal safety or the safety of others to start up the equipment if there are concerns about the electrical installation. The NEC, or National Electrical Code, is a comprehensive set of standards for electrical installations in the United States. It is updated every 3 years and provides detailed requirements for wiring methods, overcurrent protection, grounding, bonding, and other aspects of electrical safety. Several NEC articles are relevant to the concerns. NEC Article 250 covers grounding and bonding. It provides specific requirements for grounding systems, including the size and type of grounding conductors, the methods of connecting to ground, and the bonding of metal parts. NEC Article 408 covers switchboards and panel boards. It provides requirements for the construction, installation, and overcurrent protection of switchboards and panel boards, which are commonly used in MCC. NEC Article 430 covers motors, motor circuits, and controllers. It provides requirements for the protection of motors and motor circuits, including overload protection, short circuit protection, and ground fault protection. NEC Table 250.122 provides minimum equipment grounding conductor sizes for grounding raceway and equipment. The size of the grounding conductor depends on the size of the overcurrent protective device in the circuit. For example, if the overcurrent protective device is rated at 60 amps, the minimum size of the grounding conductor is 12 AWG copper. NEC Table 310.16 provides allowable ampacities of insulated conductors rated up to 2000 volts, 60 degrees Celsius to 90 degrees Celsius. This table is used to determine the appropriate size of conductors for a given load. For example, a 12 AWG copper conductor with 75 degrees Celsius insulation has an allowable ampacity of 25 amps. Therefore, it can be used to supply a load that does not exceed 25 amps. It is important to consult the NEC and other relevant standards to ensure that the electrical installation meets all applicable requirements. Failure to comply with these requirements can result in electrical hazards and code violations. In addition to the NEC, there may be local electrical codes that apply. Local codes may be more stringent than the NEC and should be followed. It is the responsibility of the electrical contractor to be familiar with all applicable codes and standards and to ensure that the electrical installation complies with these requirements. Some additional safety tips for working with 480 volts MCC include always to energize the equipment before working on it. Use a qualified electrician to perform any electrical work. Wear appropriate personal protective equipment, such as safety glasses, gloves, and insulated tools. Inspect the equipment for any signs of damage before working on it. Follow all safety procedures and guidelines. Be aware of the potential hazards and take steps to mitigate them. Never work alone. In addition to the above, consider performing an infrared scan of the electrical connections within the MCC. Infrared thermography can detect hotspots caused by loose connections or overloaded circuits. This can help identify potential problems before they lead to failures or safety hazards. Ensure that all personnel working on or near the MCC are trained in electrical safety. Training should cover topics such as lockout-tagout procedures, arc flash hazards, and proper use of personal protective equipment. Establish a regular maintenance schedule for the MCC. This should include inspections, cleaning, and testing of components. Regular maintenance can help prevent problems and extend the life of the equipment. If any modifications or repairs are made to the MCC, ensure that they are properly documented and approved by a qualified engineer. Unauthorized modifications can compromise safety and reliability. Be aware of the potential for arc flash hazards when working on or near energized electrical equipment. Arc flash is a dangerous electrical explosion that can cause serious burns and other injuries. Wear appropriate arc flash personal protective equipment, such as arc-rated suit, face shield, and gloves, when working on or near energized equipment. Perform an arc flash hazard analysis to determine the potential arc flash hazards at the MCC. This analysis will help determine the appropriate arc flash personal protective equipment that is required. The analysis should consider factors such as the available fault current, the clearing time of the overcurrent protective device, and the working distance. Follow lockout-tagout procedures to ensure that the equipment is de-energized before working on it. Lockout-tagout procedures involve disconnecting the power source and placing a lock and tag on the disconnect switch to prevent the equipment from being accidentally energized. Be aware of the potential for electrical shock hazards when working on or near energized electrical equipment. The electrical shock can occur when a person comes into contact with an energized conductor. Avoid contact with energized conductors and wear appropriate personal protective equipment, such as insulated gloves and shoes. Keep the area around the MCC clean and free of obstructions. This will help prevent accidents and make it easier to access the equipment for maintenance and repairs. Ensure that the MCC is properly ventilated to prevent overheating. Overheating can damage components and reduce the life of the equipment. Consider installing a ground fault protection system for the MCC. Ground fault protection can help prevent electrical shocks and equipment damage by detecting and interrupting ground faults. Be aware of the potential for lightning strikes. Lightning strikes can damage electrical equipment and cause power outages. Install lightning protection devices to protect the MCC from lightning strikes. Regularly test the operation of the overcurrent protective devices, such as circuit breakers and fuses. This will ensure that they are functioning properly and will protect the equipment from overcurrents. Keep a record of all maintenance and repairs that are performed on the MCC. This record will help track the performance of the equipment and identify any potential problems. If any problems are found, take immediate action to correct them. Do not delay repairs, as this could lead to more serious problems and safety hazards. By following these safety tips, it is possible to minimize the risk of accidents and injuries when working with 480 volts MCC. Remember that safety is always the top priority. Before continuing, it would be pertinent to reiterate the information provided, emphasizing the vital points. The voltage readings from the 480 volts MCC indicate a critical safety issue that needs immediate attention. The fact that the B ground and C ground readings are only 15 volts, while the ground reading is 480 volts, strongly suggests a problem with the grounding system. The electrical contractors claim that the installation is okay based on transformer configurations is likely incorrect, as these readings don't align with any standard, safe setup. The primary concern revolves around potential electrical hazards such as electric shock, arcing, overvoltage, and equipment damage. The recommended actions are firstly, to re-engage the electrical contractor with the specific voltage readings and the safety risks they indicate. It is crucial to request immediate corrective action. Secondly, create a detailed record of all communications, observations, and measurements. This documentation can serve as evidence if further actions are needed. Thirdly, if the electrical contractor does not address the issue satisfactorily, consider hiring an independent electrical inspector to assess the installation. Fourthly, as a last resort, contact the local electrical authority to report the safety concerns. When communicating with the electrical contractor, it is essential to maintain a professional and respectful tone while clearly presenting the evidence that supports the safety concerns. Furthermore, offering assistance in troubleshooting the problem can be helpful. Documenting all communications in writing and requesting a written response from the contractor is highly recommended. Ultimately, ensuring the safety of the installation is the top priority before any equipment startup. To reiterate, the key issues are improper grounding and bonding. It's likely the neutral point of the transformer is not properly grounded, leading to unbalanced voltages to ground. The bonding of metal parts within the MCC could also be compromised, creating a potential shock hazard. The next steps in troubleshooting are firstly, to verify the integrity of the neutral grounding connection at the transformer. Secondly, to check the ground conductor for continuity and proper sizing. Thirdly, to inspect all bonding connections for tightness and freedom from corrosion. Fourthly, to measure the voltage between each phase and ground at the MCC, looking for significant deviations from expected values. Also, it is vital to inspect the wiring within the MCC for loose connections, damaged wires, and signs of overheating. It is necessary to challenge the electrical contractor's claim by requesting evidence or calculations that support the safety of the grounding and bonding system. If the contractor cannot provide adequate support, it is paramount to insist on further investigation and corrections. The NEC provides the standards for safe electrical installations. NEC Article 250 addresses grounding and bonding, Article 408 covers switchboards and panel boards, and Article 430 deals with motor circuits. These articles provide specific requirements for ensuring electrical safety, referring to relevant NEC tables such as 250.122 for ground and conductor sizes and 310.16 for conductor ampacities, is crucial for verifying that the installation meets code requirements. Besides adhering to the NEC, it is important to comply with any local electrical codes that may be more stringent. Additional safety tips include firstly, always energizing equipment before working on it. Secondly, using a qualified electrician for any electrical work. Thirdly, wearing appropriate personal protective equipment. Fourthly, inspecting equipment for damage before starting work. Fifthly, following all safety procedures and guidelines. Sixthly, being aware of potential hazards and taking steps to mitigate them. Seventhly, never working alone. To add to these measures, conducting an infrared scan of electrical connections can identify hotspots indicative of loose connections or overloads. Providing comprehensive electrical safety training to all personnel involved and establishing a regular maintenance schedule for the MCC is also necessary. It is essential to properly document and approve any modifications or repairs to the MCC. Also, being vigilant about arc flash hazards and implementing appropriate safety measures, including arc flash PPE and hazard analysis, is critical. Furthermore, following lockout-tagout procedures strictly before working on equipment, being aware of electrical shock hazards, maintaining a clean work area around the MCC, and ensuring adequate ventilation are all vital safety practices. Lastly, considering the installation of a ground fault protection system protecting against lightning strikes, and regularly testing of current protective devices will contribute to a safer electrical environment. Addressing these concerns promptly and thoroughly is crucial for maintaining a safe working environment and preventing potential accidents and injuries.